Okay, in 4.1 we're going to talk about inverse functions. First we need to know what the definition of a one-to-one function is. So we know that a function is a relation such that for every valid input there exists a single possible output. A one-to-one function is a function with a special relationship between elements in the range and the elements in the domain. So a one-to-one function is a function such that for every element in the range, so we're thinking of a y value, there exists exactly one element in the domain such that we plug in the element in the domain, we get the element in the range. So that's a one-to-one function. So if we look over here, this is something like y equals x cubed. This is a one-to-one function because for any y value, we can only obtain that output on the y-axis, no matter what y value we choose for this function, from exactly one x value. Over here we have y equals x squared, and this function is not one-to-one. So let me give you an example. If we looked at the y-axis at y equals 9, so the output of 9, which is an element in the range, well, when x equals -3 and x equals +3, we get the output of 9. So y equals x squared, of course, is a function, but it is not one-to-one. Now, what this leads us to is the horizontal line test. So graphically, we can determine this property by the horizontal line test, and we just look back up here. If a horizontal line ever hits a graph twice, that function is not one-to-one. So if we look over here, you'd sweep horizontal line from -infinity on the y all the way up to +infinity on the y. So here we have the cubic function. It passes the HLT. And over here, x squared doesn't pass the horizontal line test. So that's how you can determine that graphically. That's important because the definition of an inverse function involves function composition, where we end up swapping elements of the domain and range in inverse functions. So first, let's take a look at the definition. The definition is for a one-to-one function, another function g of x equals, and we say this, f inverse. F inverse, or you can say the inverse of f. Note that this is not an exponent. That is not an exponent. Make sure we understand that that is just the notation for inverse. Okay, my favorite math word, if, which is short for if and only if. So g of x is f inverse if and only if this statement is true. So this is function composition from chapter 2. If we compose f of g of x, we get just x. So we could do a number because x represents a real number. It would match this input. Then what also has to be true is if you do composition where f is the input into g, you also get just x. So we're going to verify that f of x equals 3x plus 4 and g of x equals x minus 4 over 3 are inverses, and we do that by doing function composition. So if we need to brush up on function composition, we can take a look at that video. F of g of x, I like to write it like this more so than with the floating open dot notation. So that would be 3, and then we have x minus 4 over 3 gets replaced for the original x, a plus 4 on the outside, so you're going to see that this 3 over 3 cancels out, and then we're going to end up with x minus 4 plus 4, which is x. Okay, that's half of the definition. Now we need g of f of x. So g of f of x, here's g. We're going to take 3x plus 4, replace it for x in the function g. 4 minus 4 in the numerator there. Then we're going to end up with 3x over 3, which is just x. So we can just sum that up by saying, yes, g equals f inverse. So that is how we verify or determine. Verify means we already knew it was true and we showed that it was true. We can answer the question, just determine if they are inverses, meaning we're not exactly sure from the start if it's true or not. So let's do another one. Okay, so our functions here are x cubed plus 1 and the cubed root of x plus 1. We're going to determine if those are inverses. If they are, they will fit the definition. F of g of x would equal x, and then g of f of x would equal x. So we have to compute f of g of x. So anywhere in f, we have to put the function g. So we have the cubed root of x plus 1, the quantity cubed plus 1. So this exponent to the third power would, you'd have, if you rewrote this using exponent notation, it'd be to the 3 over 3. So I might as well just go ahead and write that, because that cubic root is radical notation. Okay, so 3 over 3 would be x to the first, or it would be the quantity to the first power, so we'd end up with x plus 1, which is x plus 2, which is not equal to x. This does not fit the definition, so we can stop there and say, so g is not equal to f inverse. So they are not inverses. Okay. Now, what if we wanted to just start from scratch and compute an inverse function? So computing f inverse requires us to understand that the domain of f is the range of f inverse. And the range of f is the domain of f inverse. So if we were to, say, take a look at something, a graph that looks like this. This is a one-to-one function. And let's say this is f of x. This is a one-to-one function. Its inverse would swap domain and range. So every y value would become an x value. And so what ends up happening on the graph is, since you're swapping x and y, it creates a reflection across y equals x. And this fits the definition of an inverse function, such that when you compose a function that swapped domain and range, you're going to end up with just the original independent variable, or whatever's inside the parentheses, which is just x. So we are going to compute f inverse for f of x equals 7x plus 1. Now, without understanding the domain and range swapping part, the steps to do this would seem kind of silly, but they're not. They're not super difficult. And now that we understand that the domain and range is going to swap, and that the domain is represented with x, the range is represented with y in our functions, this next step makes a little bit more sense. So here is where we show that we're swapping domain and range. So this x from the original is the domain of f, and we just went from function notation to y, and y and f of x are the same thing. So y is the range of f. Now, once we've made this swap, y is going to be the range of f inverse, and x is the range of f. I'm sorry, y is the range of f inverse. I said that correctly, but what I wanted to say was x is the domain of f inverse, now that we've made that switch. And it does require us, f of x does have to be 1 to 1, so I should have, went ahead and just mentioned, hey, this is a line, linear functions are 1 to 1, so we're all good, we can compute the inverse. So I'm going to solve for the range in f inverse. And once we've done that, we just want to use the proper notation to communicate it. F inverse of x is x minus 6 over 7. You could verify this by doing what we did in the first example. And that's all we need to do from 4.1.